Okay, this is the fourth and hopefully the last one on the limit definition of a derivative, or as I've put it, derivative by limit definition, whatever you want to call it. As promised, we're going to go through a couple of nasty examples, and then at the end we're going to talk about the alternate definition of the derivative. Now, let's go ahead and just jump right in with tangent x. Ew, that's not very much fun, because we talked about sine last time, and sine, of course, I had to use the sum formula. Well, I'm going to have to use the sum formula with tangent. If you remember, the sum formula for tangent's a little bit more complicated. So let's go ahead and get started. I know that the limit, go ahead and put the f prime of x right here. And we're going to go ahead and have the tangent of x plus h minus tangent x, all of that over h. Now I'm doing this one first in case I mess up, so I can do it over. I don't think I will, but you never know. So you have the tangent of x plus the tangent of h, all of that over 1 minus tan x tan h minus tangent x, all of that over h. Now, that's a complex fraction. I'm going to have to go ahead and multiply through by 1 minus tangent x tangent h. Let's go ahead and just assume that I've put that over there because I don't really have room and I don't feel like rewriting it. So we have tangent x plus tangent h, which is the numerator right here, right? And we'll put that in parentheses just for the purposes of marking it off. And of course, when I would multiply by this denominator, it would cancel out when I distributed it here, but it would not cancel out when I distributed it, here. And of course, you have to make sure that you multiply the denominator by that same factor, lest you change the form, correct? Now, that looks a little bit ugly, but once we go ahead and distribute and pull down those parentheses, it actually winds up freeing up just a little bit, such that we can actually make use of some of this stuff. Now, we have tangent x plus tangent h minus tangent x plus tangent squared x tangent h, all of that over 1 or h times 1 minus tan x tan h. Now, obviously, you see the fact that those go bye-bye, okay? And I wind up being able to factor out the tangent h, and I get 1 plus tangent squared x, all of that over h, 1 minus tan x tan h. Correct? Now, we know that 1 plus tangent squared is going to be, anyone? Secant squared. That's one of your Pythagorean IDs. Okay? But what I'm also going to do as I simplify is I'm going to take that and I'm going to break it apart and turn it into sine h over h times 1 over cosine h times secant squared x over 1 minus tan x tan h. Okay, did you see that? So this right here came down as secant squared. This still remains right here in this denominator, and this got split up into those two. Well, here's the thing. I can now plug in, at least over here, because I know that by identity, as h goes to 0, that goes to 1. I don't even have to do this other one by identity because I actually can evaluate cosine at 0. It goes to 1. And when I go ahead and plug in 0 for h, this term right here goes to 0, and I simply get secant squared over 1. So the derivative of tangent is secant squared x. Now, isn't that nasty? Thankfully, in the future, you'll just be able to memorize that and move on from there, okay? Let's do another nasty one, and then I will go ahead and introduce you to the alternate definition of the derivative. Now, if I have f of x is equal to the cube root of x, and f of x plus h, of course, is equal to the cube root of x plus h, some of you are wondering why in the world that's a nasty one. Well, you can't use the conjugate per se, because the conjugate is multiplying by using the difference of two squares. The logic of the difference of two squares is not going to work here. You have to employ the logic of the difference of two cubes in order to get where we're going. Which winds up being a little bit kind of nasty. So I have x plus h to the 2/3 plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3. Okay, and why in the world am I using that? I'm so glad you asked, okay? Because here's the thing. I remember that x cubed minus h cubed factors into x minus h, x squared plus xh plus h squared, correct? Okay, well what if I want to force x minus h to behave like x cubed minus x cubed minus h cubed? Well, then I just call x to the 3/3, and h to the 3/3, and then all I have to do is mimic the style right here, and I get x to the 1/3 minus h to the 1/3, x to the 2/3 plus x to the 1/3, h to the 1/3 plus h to the 2/3, and that's kind of how I worked backwards from this expression in order to actually know what I needed to multiply by and use the logic of the difference of two cubes. So it's not the conjugate, but it's conjugate-ish, right? Aren't you so glad that you wind up being able to do this in a much, much easier way after we put you through the, of course, necessary torture of doing limit definitions of derivatives? You're like, necessary? Yeah, it actually is. It actually winds up being incredibly necessary in terms of being able to move forward and understand conceptually what's going on in calculus. Because every time you take a derivative by shortcut, this is actually what's going on in the background, okay? Now, I could go off and wax eloquent about that, or of course eloquent is in the eye of the beholder, but let's go ahead and simplify this. Now I know that this is going to simplify in the numerator to h, which of course is going to cancel with this h, and when I plug in 0 down here, what I'm going to get is I'm going to get 1 over x to the 2/3 plus, okay, notice that that's going to be another x to the 2/3 once that h evaporates and becomes 0, plus x to the 2/3, or 1 over 3x to the 2/3. That, I mean, it wasn't that many steps. It's just that, you know, who in the world is going to think about this before they've actually been shown that, you know, short of Gauss or somebody like that. Now, those are two nasty, nasty examples. If you stayed with me on those examples, then of course I'm assuming that you're understanding this material to an adequate extent and should be able to sort of move forward and do all sorts of fun stuff that your teacher is going to want you to do in terms of working these out by limit definition. What we want to do now is I want to introduce you to the alternate definition. Now, remember that f prime of x is the limit as x approaches 0 of f of x plus h minus f of x, all of that over h. And you're like, okay, I get it. But of course, repetition is pedagogically advantageous. Now, if I want to evaluate the derivative of f at a particular value. I could just use function notation, keep the limit as h approaches 0, and this would be f of a plus h minus f of a, all of that over h. That is basically kind of like a corollary of the original definition. That is not the alternate definition. The alternate definition is the other way that you're going to find the derivative at a particular value. And that's the limit as x approaches a of f of x minus f of a over x minus a. And that should make sense, okay? Because you're still dealing with, right, y2 minus y1 over x2 minus x1, where the difference is evaporating and going towards 0, right? If x is going towards a, then this denominator and this numerator are getting closer and closer and closer numerically, because these are two ordered pairs, right? F of x is an ordered pair in general, and this is a very specific ordered pair. And so what is happening here is you're getting these two ordered pairs, and they're starting to coincide, just like P and Q on that Wolfram demonstration that I showed you, okay? Let me show you what this looks like. If I give you f of x is equal to x squared, and I want f prime of 2, okay? What I'm going to do is I'm going to say, well, f prime of 2 is equal to the limit as x approaches 2 of f of x minus f of 2 over x minus 2. But I know what those are. I don't have to be in suspense about what f of x is. F of x is x squared. F of 2 is 4. And oh my gosh, that obviously is going to simplify very easily and become x plus 2 once I factor that numerator as the difference of two squares, and that is going to be equal to 4, okay? But that's usually not how it's asked. They don't give you the function and then ask you to find it. What they do on the AP exam is they ask you a question about limits, and they don't even tell you necessarily that it is a limit. They basically say, okay, the limit as x approaches 2 of x squared minus 4 over x plus 2, or no, x minus 2, sorry, x minus 2. Now that's easy enough to evaluate. We just did, okay? But what if you were given the limit as x approaches pi over 2 of sine x minus 1 over x minus pi over 2? That's a little bit more difficult, unless you recognize that this is indeed the limit as x approaches pi over 2 of sine x minus sine of pi over 2 over x minus pi over 2. Once you recognize that 1 is sine of pi over 2, then here is your f of x, and here is your f of a, and this is your x minus a. But you have to recognize it. So the moment that you recognize this, what you're saying is that, oh, so what you're really asking me is, what is f prime of pi over 2 when f of x is equal to sine x? And really, that's the only way you can really do that problem. So basically, some problems you really won't need to be able to recognize the alternative definition, but in this one it's absolutely pivotal, because what it's saying is f of x is equal to sine x. And of course, from what we did in the last lecture, you should already know that f prime is cosine of x. So what that limit is really asking is, what's the cosine of pi over 2? And we know it's 0. But do you know that on the face of it when you're presented with that particular limit? And the answer is no, unless you see through the notation and recognize it as the limit definition of a derivative. Okay? And once we get into AP review next semester, Lord willing, we will go ahead and talk a little bit more about that, and we'll sort of go through more examples and whatnot. But I wanted to at least mention it right now, just in case she actually asked you a question on not only the limit definition, but the alternative definition. The alternative definition is very, very easy. If you have any questions on it, please do feel free to email me or comment, or we'll talk about it on the Skype session coming up on Saturday. But this brings to an end sort of our discussion in terms of the limit definition of a derivative. I hope that it's been helpful. I don't know how many videos I'm gonna require in order to get through the next section. I don't think it's going to be particularly long, but I will start right now on figuring out videos on 2.8, which is the derivative as a function. Okay, and I will be talking to y'all on Saturday. Bye.